Welcome. Today we'll be going over a proposed lumped electrothermal model for a battery module with a novel hybrid cooling system. So getting into it, we're going to do a quick little recap of the scenario that we're facing here. On the top figure, we have a cross-sectional view of an individual battery cell. It has flow channels that provide active cooling and PCM chambers that provide a form of passive cooling. On the lower figure, you will see a complete battery module that is composed of 12 different battery cells. For this model, we developed a thermal resistance diagram as seen on the right-hand side. On the leftmost node, we see the battery node that undergoes both convection and conductance. Convection in the form of natural convection between the battery and the air, and conduction will be directly between the cooling plate surface and the battery surface. Once in the cooling plate, there is another form of convection, this time forced by the coolant, and another form of conduction that is between the cooling plate and the phase change material. It is important to note that these resistances will change over time and will not remain constant. For our simulation, we used MATLAB to develop a thermal model that depicted the thermal behavior for a battery cell over time, as well as the heat transfer within the batteries and the heat transfer within the cooling plate. And these three models combined into one, which yielded us our final result on the right-hand side. In the top graph, we will see the temperature behavior over time for each individual battery cell. And as we can see, at lower temperatures, the temperature for each cell in a module is roughly the same, but as time goes on, they begin to diverge greatly. And this is due to the PCM going through the phase change and acting as a heat reservoir.
In order to analyze the thermal properties of the battery pack during normal operation, 3D computer modeling was used. This paper wanted to compare the efficiency and accuracy of 2D lumped models with 3D detailed models and determine the best method for their applications. This paper, along with other research, supports that a lumped model like the 2D model in Simulink is satisfactory for producing quick and accurate results like the 3D model in ANSYS. This report attempted to verify the findings of the paper through representation by 3D CFD with multi-scale, multi-domain modeling. From the ANSYS modeling, the temperature distribution and potential difference contours were analyzed to verify the paper's findings. In the top, we have the static temperature profile, with most heat being in the middle to the end, which is going to be the left side, with a maximum temperature of 330 Kelvin and a minimum temperature of 300 Kelvin. It's not seen right now in the picture, but we had cooler temperature profiles on the ends due to natural convection. On the bottom, we have a potential energy field. The negative terminal is indicated by the blue and the positive terminal indicated by the red, with the largest potential in the middle being green. So the comparison of these simulation models to the experimental resulted in that the results of the report were accurate. The CFD models took the most time to computate, about 30 to 125 minutes, while the lumped models for Simulink took less than 2 minutes. The temperature profiles of the 3D detailed model matched the experimental, with most heat being in the middle and near the end of the battery cell pack. They had cooler ends due to the natural convection. The coolant temperature was coldest at cell 1 and hottest at cell 12, which was also accurate with the report. And then the hottest temperature profile was on cell 6 due to less convection due to heat transfer. There was a max error of 4.5% between the CFD and experimental for cell 6 temperature profile and a max error of 1.3% for cell 12 temperature profile, with the maximum potential difference of the paper showing 0.03 volts and the ANSYS model showing 0.083 volts.
For the market overview, in 2022, more than 750,000 electric vehicles were sold. This was 57% more than in 2021. In the next 10 years, the electric vehicle market is forecast to have a CAGR of 17.3%. Moving on to the licenses and permits, there are 6 main licenses and permits I'll be focusing on. First being the Articles of Registration filing fee, which is actually free in 2023. Second being the LLC business entity. Third, website, domain, business domain. Fourth, statement of information fee that has to be filed within the state of California. Fifth, LLC annual tax. Sixth, we had to actually do a business license in Pomona, which gave us a commercial rental tax and manufacturing and processing employee tax. Next, for annual operational costs. The report goes into more detail, but for the sake of the simplicity of this presentation, we'll be going over the 9 most important, being the rental expense, amount of commercial rental tax, utilities, insurance, salary and wages, amount of manufacturing and processing employee tax, our marketing, supplies, and quality control, all being annual besides supplies, which is per unit. Lastly, we have our break-even point. So we priced our product at $9,000 with a fixed cost of $233,000, a variable cost of about $1,300, a total cost of $272,000, a revenue of $270,000, which led us to a BEP point of 30.2, which means that in order to break even, we would have to produce 31 units. As you can see on the graph, the red line, which represents our fixed cost, is straight across, which is exactly what we were expecting. Our variable cost increases slightly over the amount of units that we produce. So overall, this is kind of what we expected.